Hey guys, today we're going to check out eigenstuffs, eigenvalues and eigenvectors. So when you're watching this video, I assume that you have a basic understanding of eigenvalues and eigenvectors in the first place, but let me just jumpstart the explanations with a quick definition. So we have a matrix A. If A is a square matrix, lambda is an eigenvalue of A. If there exists a non-zero vector x such that ax equals lambda x. Basically, the transformation which is applied to vector x by the given matrix A only results in a scaled version of the same vector x. So starting out with the equation ax equals lambda x, we have a challenge because we have two unknowns here, lambda and x, and we want to solve for one first so that we can move on with our calculations. And we can do a little hack here to make it easier. So first of all, we move lambda x to the left side of the equation, and then we add an I inside here for the identity matrix. And we add in the I so that we can explain it as matrix vector multiplication as opposed to scalar vector multiplication. Since I, as the identity, is neutral in linear algebra and can just be added in. Then we have this equation a minus lambda I times x equals 0. And since we're only interested in non-zero vectors, we know that this matrix has to be singular. And we also know that singular matrices have a determinant of 0. So we can just get the determinant and set it to 0. And what happened now is that we kicked out x of the equation and we only have lambda left. Great, so let's move on. Okay, let me define a sample matrix over here, like 3, 1, 1, 3. And the identity, as we know, has 1s on the diagonal. Let's move on. So let's first apply a minus lambda I, which would lead to this matrix, 3 minus lambda, 1, 1, 3 minus lambda. Okay. Next, let's apply the determinant to a minus lambda I, which will result in 3 minus lambda squared minus 1. Okay, moving on. Next, we can further expand this result, which will give us lambda squared minus 6 lambda plus 8 equals 0. So a quadratic polynomial. And we can solve this. So to solve it, we can use the quadratic formula as shown over here, or we can factor it, and the resulting lambdas are 2 and 4. Okay, after this theoretical background, let's also walk through the same steps in Python Sympy. So first of all, we would load Sympy as SP. We would load the symbol, like the lambda over here, as a lambda symbol, and define the matrix A. So I'm loading the same matrix, 3, 1, 1, 3, and defining the identity matrix over here. So sp.I 2, because we have a 2 by 2 matrix. Then construct a minus lambda I and write it to a variable over here, a lambda I, and then compute the determinant. So just use the function .det over here, the inbuilt function, and we can factor it over here, use the inbuilt factor function. And then to get the eigenvalues, use sp.solve with these values. And when we print it, we get the eigenvalues from SympySolve 2 and 4, the same ones that we got before. Okay, great, moving on. So we did find the eigenvalues now, both in theory and with Python. And now next step is to find the eigenvectors. How do we do this? So we do use this equation, a minus lambda I times x equals 0, and we substitute lambda into a minus lambda I. So we have two lambdas and we substitute both step by step into this equation. This gives us a minus 2i, and when we calculate this, it will result in the matrix with all 1s. And now to find the eigenvectors, all we have to do is set this equation to 0 to find the null space. If you don't remember how to find the null space, please check out this video where I explained the steps. But assuming that you know how to find the null space, we will get the following result. So for the given matrix, the null space is -1 and 1 for lambda equals 2. Now we do the same calculation with the second eigenvalue that we found. We also use it to substitute it into the given formula and then find its null space. So first of all, we use lambda equals 4, and we get this matrix over here, minus 1, 1, 1, minus 1. And when we find its null space, we get 1 and 1, the vector, for lambda equals 4. Great. And now let's also find the eigenvectors with Python Sympy. It's super easy. So we stopped over here getting the eigenvalues. And now to get the eigenvectors, all we have to do is write dot eigenvects. And this returns a list with all the eigenvectors. We can iterate over this list over here and then print out the single eigenvectors. And as you will see, we get the same eigenvectors as we got in the calculation before. So it's minus 1, 1 for lambda 2 and 1, 1 for lambda equals 4. That's all that I want to show you for today. Thanks for watching. Don't forget to like and subscribe, and see you again soon on this channel.